our domain for our exponential was 0 to 1, so that our range was 1 to e. And similarly for the logarithm, we'd really like to have a domain of 1 to e. And so we can actually do that because of the properties of the discrete base, as I described them. We can actually have extra elements in the discrete base as long as they meet the conditions, and so you can duplicate any element in that discrete base any number of times, and it still is a valid discrete base. So what we can do is we can just perform the first iteration twice rather than one time, and that actually extends our domain for the exponential to more than the high end of it to more than 1, which is convenient. If you want to extend the range more than that, though, you don't want to repeat the first iteration any arbitrarily large number of times. So what you want to do is some sort of argument reduction. And in general, this is tricky to do without loss of precision. There's a whole lot of research on that. There's a whole chapter. There's this book. I was citing the references: Elementary Functions, Algorithms, and Implementation by Jean-Michel Muller. And this is a fantastic book for learning about algorithms for all of the elementary functions, including exponentials, logs, trig, and so forth. Highly recommended. There's a whole chapter in it on how to do argument reduction and the various problems you can run into. It's very easy to lose precision. However, if you do this in binary arithmetic, and if you're doing logs and exponentials with a base of 2, then your argument reduction becomes simply shifting to the left or right, and so therefore it's sometimes advantageous to actually do. If you want a log base e or a log base 10, you may want to actually use a base 2 logarithm instead, and you just multiply the result by a constant to get the log base e or the log base 10. So that's actually done in some math libraries on general purpose computers. I already mentioned that it's pretty easy to do this for log base 10 instead, other log bases. This slide isn't about this. This slide is about doing the arithmetic and other bases. If you want to do the arithmetic in base 10 like is done on calculators, use your discrete bases based on 10 to the minus I instead of 2 to the minus I, which means you still do your multiplication by powers of 10 by shifting. And to preserve the properties of the discrete base, then you do need to use each of those entries in the table more than one time. So performance. Shift and add algorithms are great for hardware implementation, like in FPGAs, and it's actually even possible to optimize this even further in hardware by using what's called a redundant arithmetic representation. I'm not going to go into detail on that. Software implementation is very good on processors that have barrel shifters, which almost all modern processors, 32-bit and up, do. So microcontrollers based on MIPS and ARM. This is a good algorithm. On processors that have high performance floating point addition and multiplication, like an x86 would, you're probably better off with polynomial or rational approximations. And of course, if you're doing that, there are a ton of high quality libraries already available, so you wouldn't need these algorithms in that case. So the logarithm algorithm of the two that I presented here is actually very similar to what was invented by Henry Briggs in 1624 that he used to produce tables, only 10 years after the logarithm was actually invented. 1962, Meggett at IBM proposed doing this in a similar fashion. He called the iteration pseudo-division because it has some similarity to the long division process. Decimal version of this calculator is used in most or maybe all HP calculators starting from 9100 desktop, 1968, HP 35 handheld in 1972. Jacques Laporte gave a very detailed explanation of the algorithm exactly as used in HP 35 on his website. I'll cite that in the references. He also explained why the HP 35 logarithm error, which they had a ROM upgrade to fix, why that happened. There are related shift and add algorithms. Some of you may have heard of Cordic, which is pardon me, an algorithm used primarily to compute trig functions. It turns out because the exponential of a complex number, you have Euler's equation that says e to the ix is cosine of x plus I sine of x. You can use the same algorithm but in the complex plane instead of just the real number line to compute the trig functions, and that actually is in some ways better than using Cordic. It has some advantages over Cordic, although it needs larger tables. I've got a spreadsheet on my website that shows how this works, all the iterations to compute this to 12 decimal places for values that you can enter into the spreadsheet. And some references. I already mentioned the book. There are a few other references, and you'll be able to get all this from my website. Any questions? Yes.
Can you just quickly run us through how I would calculate, let's say, e to 100? Because I didn't quite get how you move from like that small domain of 0 to roughly 1.2 if you want to have the x value to be 100.
Yeah, I glossed over the how you do the argument reduction. Basically, you have to use some identities to do that, and I don't really remember the details because I haven't been focusing on that part of it. Sorry. This book has, as I say, a huge amount of information on that. Yes, Richard?
What do you have for the square root in this machine? For square root? Is it?
The square root is usually done using an algorithm that's similar to long division.
Yeah, I mean, in like at least in the 41 and
But
related.
you have a fast way to efficiently calculate square roots?
This particular algorithm doesn't do that. Although I suppose you could use a log and divide by 2 or an exponential to do that. But there are other algorithms for that. There's actually a variant of Core that can do that, but that's not the most efficient way to do it.
It takes 4 iterations to get 12 digits of a square root.
Yeah.
On a decimal machine.
Well, if you can do a square root, it turns out there's a way to do logarithms that actually converges quadratically. That means that each iteration doubles the number of digits of precision. And if you would like to know, I'll tell you what it is.
Okay, well, yeah, that would be interesting.
It's incredibly simple. We were talking at breakfast about percentage change, and I was saying that the way they calculate percentage change in the calculator is all wrong, because if you go from 1 to 2, that's a gain of 100%, but if you go to 2 to 1, that's a loss of only 50%. Well, that's very inconsistent. And the financial people who are trying to bamboozle us always use that trick to distort their statistics. So what you really want to do is divide by some number that's between 1 and 2. Use some number between 1 and it turns out, so if you use the arithmetic mean, that's a big improvement. You go up and down the same amount. But you still cannot add percentages. It turns out if you add percentages that way, you get a certain error. Now, if you use the geometric mean, you get a smaller error. And if you then use the average of the arithmetic average of the arithmetic mean and the geometric mean, you get less error. And it turns out there's something Gauss developed called the arithmetic geometric mean. You ever heard of that?
Yes.
And it turns out if you divide x minus 1 by the AGM, that's the natural log. And the AGM converges quadratically. And I bet that would be a lot better than what you got now. But in order to do it, you need a quick and efficient and accurate square root.
Okay, that's worth looking into. You have a question, Jeremy? No. Oh, okay.
There's
Yes.
another reference, I don't know if you've seen it, the software manual for the elementary functions
Yes.
by Cody and Wade.
Yes. All right. We have the lights. So I've got the DIY four hardware as well as a 2 and a 3 here that people can look at, and I'll also show. I mentioned the eval board that I used to start development. It costs about $300. They also have what's called a starter kit that is only about $70. It's a very cute little board. It's got an LCD display, and it also has the USB debugging. You can either run it from USB or from a coin cell, and it has a demo. I can show you later that has a kind of a touch slider here, and also this has the energy monitoring where you can get a waveform of what your power consumption is, but it doesn't show it on this display. You get it over USB on your computer. So if anybody wants to play with these microcontrollers, is a nice inexpensive way to get started on it.
That doesn't include the controller.
Sorry?
It doesn't include the controller.
What controller?
It's plugs in there?
No, this is everything.
Oh, okay.
All you need is this board. You plug it in, but it comes with the USB cable. You plug it in your computer. It also comes with
Power's on the USB then.
yeah, and it also comes with a evaluation or it comes with a version of a Windows-based cross-development environment with C compiler and assembler and everything that is limited in what, you know, because it's free. They limited what size program you can link. But there are other, you can use any ARM development compilers you want. This is just, you know, one that they throw in with it that's free.
Do you have the names of this as a reference in your presentation, the proceedings?
In your notes that I...
It's in the notes. It's not currently the proceedings because I only got these presentations finished last night. But it'll all be on my website, and so I can give out the URL for that, and I'm also going to give it to the stuff to Richard.
What is the
It's the URL is http://www.brouhaha, it's brouhaha.com/hpcalc/HHC 2010/. And not all of this is on there now, but it probably all will be by later tonight.